Welcome back to Mr. Hassan's Maths channel. In this video I'm going to be going through a question from a mechanics paper. This is a question from a collection of questions or collection of papers called the Solomon papers, where the questions taken I think from some of the old pre-2008 papers, and this question is in the collection called Solomon K, and it also is a question on my end of topic worksheet on statics, which is also question 7 on that worksheet. So one of my students has asked me to answer this question, so that's what I'm doing right now. Okay, so figure 3 shows a block of mass 25 kilograms held in equilibrium on a plane inclined at an angle of 35 degrees to the horizontal by means of a string which is at an angle of 15 degrees to the line of greatest slope of the plane. In an initial model of the situation, the plane is assumed to be smooth. Giving your answers correct to 3 significant figures, show that the tension in the string is 145 newtons. So now they've told us that some information that we need to put in here. So first of all, the forces acting on this block are its weight acting vertically downwards, and its weight is the mass times g, so it's 25 g newtons acting down. Then they also told us that, well, we also know that when two objects are in contact with each other, okay, there's going to be a reaction force which acts perpendicular to the plane in which they're in contact. So this is going to be the reaction force acting upwards here, perpendicular to the plane. They also told us about tension in the string. So the string is inclined at 15 degrees, so that's the tension in the string, okay, which we have to find for part A. And that's everything we know. We know there's no friction, so there's no frictional force acting either down or up, depending on the situation. There's no frictional force going to act. There's going to be no resistance to the motion by friction. Okay, now, what we need to do here is we need to resolve the forces in a direction parallel and perpendicular to the plane. That always makes life easier. So what I'm going to do is I'm going to draw some dotted arrows to show that this is not a new force, this is just the resolving of these forces parallel and perpendicular to the plane. So this angle here is 35 degrees. Through similarity, these two angles are the same. I think I've explained in one of my other videos exactly how that works. Basically, you have a pair of similar triangles. Okay, the triangle that this makes with the plane. Okay, this line of force and the weight makes with the plane. These two triangles are basically similar. Okay, and I can explain why this big triangle and this little triangle are similar. This angle is the same in both these triangles. This angle is the same in this big triangle and in this little triangle. And also this has a right angle, which is, there's a right angle there, there's also a right angle here. Okay, so therefore, I mean in this place here, so if this is 35, this is 90, and this is 35, and that's 90. Sorry, if this angle is the same angle in both of these big triangles, in both this big triangle, this little triangle, and this is 90 here, and this is 90 here, then you've got the third angle must be the same, which is 35. Anyway, I've gone through it in more detail in one of my other videos. Now, so you have 35 times, now you're going into the angle, it's going to be, sorry, not 35, 25g times, that's the force, times, you're going into the angle, cosine 35. And here you're going away from the angle. If you want to resolve this force going away from the angle, because it's 25g, this line of force has to go away from the angle 35, this is going to be 25g. When it's going away, it's sine 35. That's a nice, neat way of doing it, instead of having to, make a triangle and resolve. It's an easy way to remember. Same thing here, the tension. Also, I'm going to resolve it parallel and also perpendicular to the plane. Okay, so this is going into the angle, so it's cosine, so this is 2t times cosine 15, and this is going away from the angle that we're given, so this is t times sine 15. So now we have all the forces resolved and acting on this particle. So we want to find the value of t, so we're going to resolve parallel to the plane. So I'll just show the steps here so that we can see what's happening. So if we resolve parallel to the plane, you're going to have t times cosine 15. Now, if it's in equilibrium, that means the resultant force on this object is 0. So that means the force acting parallel to the plane up and down will balance each other out. So t cosine 15 must be the same as 25 g sine 35. Okay, the reaction force has no component parallel to the plane because it itself is perpendicular to the plane. So simply to find t, we have to just do t 25 g times sine 35 over cosine 15, and that will give us a value of t. So let's just stick that in the calculator and we should get the answer. So we have 25 times g, which is 9.8, times sine 35, just to make sure we're in radian degree mode, yes we are, over cosine 15, and that gives us 145.483, 145.483, and we have to round to 3SF. It tells us here, yes, that's correct. Okay, let me just do something here. I showed these steps on that side because I wanted to see the diagram in front of me. So what I'm going to do is I'm just going to just drag all of this down if it wants to come. No, it doesn't want to come. Let me see if I can do it one more time. Doesn't want to come. Okay, let me copy and paste it down. Now I wonder where it will paste. Hope it pastes exactly where I want it. Yep, okay, good. All right, so that's where you should really show your working, not all clumped up in one corner. I just wanted to be able to show the diagram. So then we round our answer to 3SF. So it's 145 newtons, and that's the answer to 3SF. And we've shown it very clearly with these steps. Then it says, find the magnitude of the reaction between the plane and the block. So we've got to find the value of R. Now, if you look at the block and the forces acting on it perpendicular to the plane, you've got the reaction, and you've also got the component of the tension acting up the plane, acting perpendicular to the plane. Now it's very important. A lot of students, they just think R is equal to the component of the weight acting down. So they'll say R equals 25g cosine 35, and they will lose lots of marks from that. Okay, you have to be very careful. Okay, because sometimes one answer in a mechanics question, other answers also depend on it, and sometimes they don't have this error carried forward. So you'll lose all the answer marks, even if your method marks were correct, from the point that you made that mistake. If it will cause all your other answers to be wrong if it's a question that has lots of parts, and sometimes the answer affects other parts. So you be very careful. So we can see when you have an inclined plane and you have another force acting which is not parallel to the plane, it's inclined, it's like inclined like this tension, it's going to have a component that's parallel and perpendicular to the plane as well. So we can see that if this is an equilibrium, that R plus T sine 15 must be equal to the component of the weight perpendicular to the plane, which is 25g cosine 35. So R plus T sine 15 acting upwards perpendicular to the plane must be equal to 25g cosine 35 acting downwards perpendicular to the plane. So we're going to resolve the forces here perpendicular to the plane, and as we said, R plus T times sine 15 is equal to 25g cosine 35. Just make sure that we mention that correctly. R plus T sine 15 equals 25g cosine 35. That's correct. Now we know what T is already from here, so we can just replace the T with that. So we're going to have 25g cosine 35 minus 145. I'll put the more accurate version of it in here so we can show we're keeping accuracy. So R is equal to, and then so let's just put this as we already have it. multiply this by sine 15, and that gives us, that's the answer in the calculator now. So what I'm going to do is I'm just going to type 25 times 9.8 times cosine 35 times cosine 35 and minus the answer that we had, and that gives us 163.038. 163.038. So we can say that the reaction force to 3SF, as they ask us to write it, is equal to 163 newtons. So that's the answer for part B. Okay, so that's the answer for part B. Find the magnitude of the reaction between the plane and the block. That's right. Okay, all right, so now to part C. In a more refined model, the plane is assumed to be rough. So now we have to deal with friction. Okay, very important. Rough means friction is involved. Given that the tension in the string can be increased to 200 newtons before the block begins to move up the slope, find the correct to three significant figures, the magnitude of the frictional force, and state the direction in which it acts. Okay, so we've got to find the frictional force that acts when the tension is 200 newtons. Okay, so the tension is 200 newtons. That's going to be acting, let me put it as a solid line so that shows that it's the actual force. So that's the tension of the string, which is 200 newtons now. So we know this is 200 newtons. Okay, of course, we still have the same weight of block. We still have the reaction force, but we have an extra force now as well, which is the friction. Because that's the reaction force, and that's the weight, which is 25 G newtons. Okay, but there's also another force that we have to consider, and that force is the frictional force. Okay, now how does the frictional force act here? Well, it says, given that the tension in the string can be increased to 200 newtons before the block begins to move up the slope. Okay, it says up the slope. So it's about to move up the slope. Okay, all right. So 200 newtons is like the limit of this before the block moves up the slope. Okay, so basically, if the block is trying to move up the slope when the tension is 200 newtons, then the frictional force is going to be opposing that motion. Friction always opposes the motion that's happening or is trying to happen. So the frictional force has to act down the plane in this case, because it's about to move up the plane. It's going to be pulled up the plane by this force. This is going to oppose the motion. So that's what we have to take into account. So let me now just put all the forces resolved. So this is the weight resolved in this direction and the weight resolved in that direction. The tension resolved in perpendicular to the plane and parallel to the plane. So this is 20, this is T, this is 200 times into the angle cosine 15, 200 away from the angle sine 15. Remember, this is 35 degrees. This is 25 G going into the angle cosine 35, and 25 G going away from the angle sine 35. Okay, so what we can say is, now we want to find the value of the frictional force here. So we know that if it's about to go up the plane, let's take up as positive. We've got 200 cosine 15 acting parallel to the plane upwards, must be the same as, okay, the frictional force, which you have to find, plus 25 G sine 35. Now remember, this is still in equilibrium because it says it can be increased to 200 newtons before the block begins to move up the plane. So that's like the limit. So it's still in equilibrium. So if we just rearrange this, we have all the information we need except for the friction. We can just rearrange this and find what the friction is. It's going to be 200 cosine 15, take away 25 G sine 35, and that will be our frictional force. So let's just calculate that. You've got 200 cosine 15 minus 25 G, 25 times 9.8 times sine of 35, 25 times 9.8 times sine 35, yes, and that gives us 52.6589. 52.6589. 52.6589 ... So we want it to 3SF, as I mentioned again here. So it's 52.7. 52.7 newtons, and there's the answer. And then it also asks us something else, and you've got to be very careful not to miss it out. It says, and state the direction in which it acts. Okay, so of course we've shown it in the diagram here that it's going to be acting down, but we should mention it here as well. It's acting down the slope, Okay, down the slope. Not up the slope, down the slope. Okay, so there we have the answer to part C. Okay, now part D says, without performing any further calculations, state whether the reaction calculated in part B will increase, decrease, or remain the same in the refined model. Give a reason for your answer. Well, remember the tension before was 100 and something. It was less, 145. So the tension in part A, or part B, the tension we found in part, I think it was A. Yeah, tension in part A was equal to, actually it was, the tension in part A was 145 newtons. Okay, and the tension in part C is 200 newtons. Okay, so basically the tension has increased. So if the tension increases, then basically what happens is the component of the tension acting perpendicular to the plane upwards is also going to increase. So this has got bigger than it was before. Okay, before it would have been 145 sine 15, now it's 200 sine 15. Okay, so this is actually bigger now. Okay, so this component of the weight acting down is the same, it hasn't changed. Okay, and the force R plus this must be the same as that. R plus 200 sine 15 equals, or R plus T sine 15 is equal to 25G cosine 35. If T increases, okay, then R must decrease because they both have to add up to the same thing. So I hope that's clear. If the tension increases, then this increases, and therefore the share of R has to be less. Basically, you can think about it logically. If you increase, like if you're holding a suitcase on a ramp, and you kind of increase the pressure or increase the tension that you're pulling up with, then it's going to have less of a contact with the floor. The contact of the floor will become lighter, so the reaction will become lighter, you can say, because it's the thing that's acting this way is its weight. Okay, it's the component of its weight down perpendicular to the slope. So what we can say is we can say R will decrease. R will decrease. Okay, you state the answer first. Okay, it says state, so we're just stating. And then we're going to give a reason. You can say as R and the component of T must come to T up or perpendicular to the plane, sorry, my bad handwriting, must be equal to the component of the weight of the object. I'll just say the weight perpendicular to the plane. I'll write perpendicular like this. Therefore, if T increases, R must decrease. Something like that is fine. Okay, it doesn't have to be a whole essay like I've written here, but this is fine. Okay, so I hope you understand, because T 200 sine T sine 15 plus R must equal 25G cosine 35. If this gets more, then this has to get less because they have to add up to the same thing. Okay, so there's the answer to part D. Okay, apologies for my bad handwriting in this question. Thank you for watching.